as you guys heard, I do work on the MIC project and a few other projects. I like to kind of really classify them all as assay development, which you can kind of tell from my title here, which I'm going to talk a little bit about my academic development and then some of the research that I've done throughout the years. Of course, before I start, I'd like to thank the NSPIRE program, all the participating universities, the North County Higher Education Allowance for getting this all together, and of course, all of you who are taking time out of your day to go ahead and participate and watch this presentation. Hopefully, you'll get something out of this that might help you make some big decisions in your life. Looking back at my life, I never really saw myself as someone who would be getting into research or STEM in particular. I was mostly just bouncing around through what interested me from one moment to the next. But when I look back at some photos, particularly for assay development, which is a field focused really on efficiency oftenly, I found one that kind of encapsulated that. This is a photo of me in elementary school at some point, and right away you can tell this is in a very efficient hairstyle. My mom used to actually just stick a bowl on my head, cut around it with a pair of scissors. So super cheap, super easy, only nicked my ear once or twice. But what you might not be able to tell is that this green vest and green shirt is something that I actually wore practically every day because, if you can cover your body with a piece of clothing, why would you need more than one pair? And then finally, just to put, the icing on top, I actually grew up in a military family, so there was a big emphasis on making sure everything was clean and tidy. The bed had to be made every morning. But I lived in Southern California, so do you really need blankets? So to really make my time even more efficient, I would go to bed fully dressed, sleep on top of the blanket, shoes and everything. And I could just wake up and go. And looking back, I could imagine how terrifying this must have been to enter a child's room and see him sleeping like a cyborg. But luckily, I've grown out of this for the most part, and I went on to high-tech middle and high-tech high. Those are schools, if you're not familiar, that really focus on project-based learning, working with collaborators, and coming up with ideas. Sometimes you're making a documentary, a play, a satire. Sometimes you're making some sort of physical or scientific apparatus that demonstrates a concept. So in hindsight, this was a lot of fun, and I can see how it really led me on my path to getting involved in research. I became excited about doing hands-on work where I can create a real tangible product. But I still didn't really view myself as someone that would go into a STEM field. Coming from a military family, I was thinking about actually joining the Navy, of course, and then some other maybe fields, just working more with my hands or physically as like a firefighter, perhaps. And I'd done a lot of work, landscaping, cleaning pools, and I had liked doing more physical labor. But I was interested in going to school, and I was terrified of, taking out these loans. If you don't know exactly what you want to do, I'm not sure I want to pay thousands of dollars to figure out if it's right for me. But luckily, there was the CalVet fee waiver, which I'll talk about on the next slide, which was a way for tuition to get waived at Californian schools. And this was really impactful because it allowed me to take this risk to go to school. And I applied to several different universities and was able to get accepted to San Diego State, which was a really fantastic opportunity for me. For the information for those that this might be, you might be eligible for, the college fee waiver for veteran dependents allows you to waive tuition at state community colleges, state universities, as well as the UC campuses. So, this can be incredibly valuable because, university can be very expensive. In my case, there are several different ways you can be eligible, but in my case in particular, my father had received a disability as a result of his service, which allowed me to classify as being a dependent of my father. And if you at any point in your time in school think that this might apply to you, you can go ahead and apply for it. And you do so annually to waive the fees for that year. So even if you're already in school and you think this might work for you, I definitely think you should look into it. Of course, you still have to pay campus fees, but I was able to do a lot of that payment through, pool or working at a pizza shop, which is also real kind of personality builder when you're cleaning out drains full of cheese. It makes research struggles seem a little bit better in comparison at times. So definitely good to get your hands dirty with some work too. When I got to San Diego State, though, I was really caught off guard by the fact that I had been so used to project-based learning and presentations that when I stepped into a classroom of 500 students and the real metric for looking at our success was an exam score or a grade, I found it hard to get motivated for those things, and it was a real disconnect. And actually, I had gone into my first math exam and immediately failed it because it didn't really cross my mind to study for something. I was used to doing things more practically. And as a result, I realized, okay, I need to change my method. And I sought out this program that's available at San Diego State and a lot of other high schools and colleges called the MESA program, which is the Mathematics, Engineering, and Science Achievement Program. If you're not familiar with this, it's likely that there's a program very similarly to it at your institute or school, and I highly recommend you look into it because they can really give you a lot of structure and guidance that you really need at this early stages in your career. In particular, they have academic planning. You can talk to mentors. You can talk to people working in different fields. There's shadowing opportunities. And you can really ask these questions that can define the rest of your life. There's internship and job opportunities. And in particular, what helped me with my academics were the workshops and tutoring opportunities. So a workshop is a small class, somewhere between 20 or less students. And it follows really the coursework of what's going on in a major course. So you leave the 500 student course, you go right after it to a smaller course that's taught by a student that previously took it. And you can actually work really closely with students and work and tutor with one another. And I found this to be really exciting because I didn't really have trouble grasping the material. I just wasn't motivated enough to go ahead and study. But this gave me a reason to do so. And I was really excited to get to work with these other students that were maybe struggling with these topics and help find out ways to explain it to them in a more creative fashion. And that resulted in me working as a workshop instructor for several different courses, teaching chemistry, physics, mathematics. And the program also then put me in contact with a lot of the research opportunities going on at San Diego State. One in particular was working with Dr. Grotron at his organometallic catalysis lab at San Diego State University. When I was there, I worked on hydrogen fuel cell systems. You likely have all heard about hydrogen fuel cells. In our case, we wanted to do one that was photoactivatable, so it could be using converting sunlight into energy. And the main process is that you need to do an oxidation to turn water here into oxygen gas. And then with the hydrogen atoms that are left over, that gets reduced to make hydrogen gas in the other part of the fuel cell. And why you'd like to do this is because hydrogen first is a great way to store energy. Unlike transferring energy through electrical lines, for example, that loses efficiency over distance, hydrogen gas, you can transfer it all the way across the world. And as soon as you burn it, it still retains the energy that you stored in it initially. But even more excitingly for green energy is that when you combust hydrogen gas, you just get water as the byproduct. So you don't have to worry about creating all these harmful or greenhouse gases that pollute the local environment. So that was really exciting, and I really wanted to test and apply a lot of the chemistry I was learning. So these organometallic catalysts here are depicted as in this image on the left. You can see the organic part, which really refers to compounds made of nitrogen, carbon, and oxygen. All these things basically stuck to the centerpiece called ruthenium are all of the organic ligands that bind to the complex. And then the metallic part comes from, of course, this metal atom here, which is ruthenium, which a lot of metals can do really creative and interesting catalysis. So what we wanted to do was bring down the energy barrier to make the system more efficient. And right away, as you look at this mechanism, you can see there's a lot of these hydrogen atoms disappearing along the process. So what would be great is if you could have some sort of local pendant base in the system that can help pluck these guys off along the way. And that's exactly what I have depicted over here. With this nitrogen position, we were able to actually make these catalysts more efficient and lower the energy barrier and make them more stable by introducing this component and actually pull off these hydrogens along the way. So, immediately this is extremely exciting to me. I'm getting my hands dirty. I'm working with reactions in the lab and talking in an environment full of other students, graduate students, faculty, technicians, and really getting to hear their life stories and how they succeeded and got to where they are. And as an undergraduate, this can be a phenomenal opportunity because first of all, you want to know that this is even right for you. So you can figure that out quick and early by getting involved in a research opportunity. But secondly, if you do find out it's right for you, these people know exactly what the next step should be. And that's exactly what happened. They put me in contact with several different REUs and SURF programs that I could apply to. One of which I got into is the SURF program right across the street from San Diego State practically. It's in the same city. So you just drive down 8 and you're over there at that school. And it was fantastic. Like as Paul said, this is a 10-week full-time internship. You're working under the direct supervision of a highly trained scientist. who really knows their work, and you get to work with them closely and see the thought process and really figure out if this is exciting or right for you. There's weekly academic and research seminars, so you don't just get exposed to that one topic going on in the lab. You can hear people talking about nitty-gritty chemistry all the way up to using alcohol models in mice to study addiction. And of course, getting a $5,200 stipend and housing for someone that's maybe not had a full-time job can be a huge amount of money. And it can also put you in a new city where you can meet new people, which is just a good personal experience as well as one for your career. And a lot of opportunities for presentations to build your resume and hone your skills. And just like Paul said, look out for the application deadline. And if you meet these eligibility requirements, there's no reason why you shouldn't apply. And if you're lucky enough to get accepted into one of these programs, you might get the opportunity to do one of these weird photo shoots. So, and these PR guys are phenomenal photographers, but they don't know anything about research for the most part. So you just go around the lab grabbing whatever they say, and you just look at it and pretend it's exciting. So we're just holding empty vials, unstained TLC plates, and you try to look excited. My mentor here, Daniel Globish, wasn't quite able to muster the excitement to look at this vial, but he tried. But more importantly, the research that I did at the SIRF program was really awesome because it exposed me to topics I didn't even conceive. Everything that I'd done up to this point is not something you would ever want to put into a human body. It's not related to any sort of biology or treating any human diseases. And that's exactly what I got exposed to in Dr. Janus' lab. So here, the first project is a targeted nanoparticle drug delivery system for malaria. If you're not familiar, malaria, the parasite, can actually spend a lot of time in your liver and infect that site in particular. And a lot of drug companies can make their drug systems more efficient by if you can target it to the region where the infection is, you can use smaller doses, you have less side effects. And in our case, targeting liver cells meant using these sugar compounds here that are actually able to bind receptors on the surface of liver cells and help the drug get inside them in a targeted fashion. So I went ahead and synthesized these conjugate linkers and gave them to our collaborator to go ahead and test and try. And then in addition to that, I was also working on a diagnostic called for onchocerciasis, which is a parasitic disease. And this test works just like a pregnancy test. You apply urine to it, you look for a color change, and it will tell you whether or not you're infected. So both of these very different ideas, and I found it really exciting. Because for the most part, I was exposed to a lot of fairly difficult chemistry. And I found that in the field of chemical biology, you can apply a lot of rather simple chemistry techniques often and get amazing biological results as long as you have a good idea and a good target. So at the Scripps Research Institute, I eventually was able to end up here as a graduate student. I applied to grad schools right after undergraduate. I figured, hey, I could join the Navy officer program, but they're going to pay me to go to graduate school. And why not? You can always leave at any point. If you want to get a master's, you can leave within a couple of years. There weren't a lot of reasons not to. And especially when you look at the Scripps research application, which has no application fee, so it's completely free. Some other applications can be somewhere between $50 and $100, which can be a lot and start to add up. But being completely free is, no reason why you shouldn't do it. You might as well throw it in there and take a gamble. But while I've been working at Scripps, I've worked on a number of projects. Three of the main ones that I've worked on are this point-of-care diagnostic I just mentioned, which is nearly complete at this point. I do some work on and off on it occasionally when people send us more samples to analyze. The project that I've taken up most of my time is creating an assay to diagnose inhibitors for the NIC protein. This is a protein that's involved in somewhere between 60 and 80% of cancers. It really helps them grow and divide and be aggressive. So, potentially a very universal drug target. If you can hit this target, you can maybe help a lot of different cancer patients. And then finally, more recently, I've been working on another assay for inhibitors for the PDL3 and PDL4 exonucleases. These proteins are involved in the signaling pathway that modulates the immune system. So potentially by targeting them, you can make the immune system more aggressive, for example. And a lot of research points to the fact that you can use these to help target cancer cells, in addition to some of the other cancer work I've been working on. Those are very important fields to be studied. But when you look at all three of these, it's very difficult to explain them all in one presentation, right? There's a lot of background information, different techniques, different strategies that have to be applied for all these unique pathways. But what overarches all of them is this concept of assay development, which is just a fancy way of saying a test or a screen. Can I come up with a thing that shows that you're infected or not? Can I come up with a thing that can find new drugs, for example? And those are really, I can break down into 4 key points. There's the target and objective. There's a limitation of the current methodology, innovation, and development. The target, of course, does the world need this? Is it going to help people? Is it going to make things more efficient? Is it going to benefit society some way? And then the limitation, if there is this need to create an assay, why doesn't it exist? Is there no assay currently available? If there is one, is it too expensive? Is it too hard to use? What is that limitation? Is it just not accurate or reproducible? And then the real scientific portion that comes from you is how can you apply your knowledge to come up with some innovation that addresses this strategy? Can you overcome it? Can you work around it? Can you even apply a whole new strategy to the problem? And then finally, once you've done that, it's not just left there. You have to develop it, evaluate it, validate it, and figure out how useful is this thing that you created? Is it something that can actually be used? Is it accurate, reproducible, etc.? So as an example to kind of give you an idea of what this process looks like, let's talk about the onchocerciasis project. Onchocerciasis, if you're not familiar, is a parasitic disease that's primarily in sub-Saharan Africa as well as Central and South America. The World Health Organization estimates about 18 million people are infected with this parasite, and 123 million people are at risk of becoming infected. So certainly a large population. Why it gets the name river blindness, which you might be able to tell from my title slide up here, is that the river portion comes from the vector, which is a black fly. So just like malaria is spread by mosquitoes, river blindness is spread by this black fly. And the black fly gives the point of the reference river because this black fly lives near fast running water, so often rivers. So you'll come to these rivers and you'll find individuals infected with this parasite. But it gets the name blindness because this parasite mostly is in your skin, but it also goes to your eyes. And while it's in your eyes, it slowly produces damage and scar tissue that results in blindness over years. And it's actually one of the leading causes of preventable blindness. And I say preventable because there is actually a very effective drug treatment for it. Ivermectin is a Nobel Prize winning drug. It's a phenomenal drug. If you have a cat or a dog, it's likely that you've given them this anti-parasitic drug. In the case of onchocerciasis, it works by paralyzing these microfilariae, which results in them dying over time, but it doesn't target the adult worms. So if you want to really accelerate this process, you can use deoxycycline, which kills the bacteria that the adult worms are reliant on. And then with a mixture of these two, you can treat people very effectively. And luckily, through the World Health Organization, donations by pharmaceutical companies, and the Bill and Melinda Gates Foundation, a lot of these treatments are actually readily available for individuals. So that comes to the question, then what is the limitation? If we have a problem, we have a solution. It's really the diagnostic. At the time when this work was started, the gold standard for diagnosing individuals is something called a skin snip. And that requires taking 6 biopsies from a person's body, growing them and looking at them in an incubator with a microscope and trying to count these microfilariae that are in the skin. And the problem with this is if you're in an area that doesn't have readily available clinics, doctors, and trained individuals to do this kind of work, you're not going to have a laboratory or a microscope or a technician that can even do it. You need something that's going to be more readily available and easy to use. In addition to that, the detection is limited to 1.5 years after infection. So you have to be infected for a reasonable amount of time before the microfilariae are even prevalent enough in the skin to see it. And even if you are being treated and you see the microfilariae disappear, this strategy doesn't look at the adult worms. So if you're not taking deoxycycline, it's possible that these adult worms are still alive, and you want to make sure you undergo treatment long enough that they die out of natural causes. So can we improve this? And what we were hoping to find is there some sort of biomarker in your urine, for example, that we can just test your urine and tell whether or not you're infected? That would be an ideal way that you can basically encapsulate the whole human body in a single sample and view for any evidence of the parasite being prevalent or even there at low concentrations. So to do this, we collected hundreds of urine samples from individuals that are infected and aren't. And this is an image of a chromatograph. So essentially we run all these urine samples through a column. All the different molecules get separated based on their physical properties. That's kind of represented by all these little peaks here. And they're all overlaid with a bunch of different patients. And using software developed at the Scripps Mass Spec facilities core here at the Scripps Research Institute, they are able to deconvolute that and identify this peak here, which represents all these red peaks as the positive individuals. And you go down to the baseline and you can see these little black peaks here are the negative individuals. So clearly a large difference between people that are infected and not for this molecule. But in addition to just separating them, you can use a strategy called mass spectroscopy to get the mass of this. And you can not only get the mass of the complete compound, you can actually start fragmenting it. And unfortunately, the way compounds fragment is actually somewhat predictable. And in doing so, you can hypothetically build out the original structure. In doing this, we proposed this structure as NATOG. We made it and showed that it had the same physical properties as the compound that we were finding in urine. So we had then validated that this is the true compound. And then we could go ahead and make an internal standard and use it to quantify a lot of the concentration of NATOG in a bunch of different patients. So right here, looking at onchocerciasis positive individuals, you can see they have just under 40 micromolar NATOG in their urine. And you can compare that to the African and US controls, as well as elephantitis, which is a co-pandemic in a lot of these regions, as well as a few other parasitic diseases that we looked at. But there was a clear separation between people that had onchocerciasis to all of these other diseases. But which was even more exciting in a way too, was that if you look at people being treated with the oxycycline versus those who aren't, you can see a big drop in NATOG concentrations. So this means not only can you tell whether or not someone has it, but you can actually monitor the disease progression. So you know when is the right time to stop treatment, for example. And that was really exciting. So we clearly have a biomarker here that shows whether or not you are infected. The next question is, how do you use this? How do you turn it into a test? So a very common tool is what's called a lateral flow immunoassay. This is something that's often used in pregnancy tests and things that are like that. It has four main components: a sample pad, this is where you apply the urine, antibody gold conjugate or some sort of antibody conjugate here. You have a test line where you actually put the conjugate, in this case NATOG, and you immobilize it at this point. And then a wick pad, this is just an absorbent pad that will pull the liquid across. So the key components are really this gold conjugate with antibodies and this test line. Antibodies, if you're not familiar with them, they're basically molecular tweezers. They can really specifically and selectively pull out really unique compounds out of mixtures, even if there are similar structures. They have this remarkable ability to pick them out. And as a result, we can kind of use this as a way to specifically grab NATOG and show whether or not it's there. And by coating them with gold nanoparticles, you can start to visualize it and really see where they are. And I'm going to show you why that's important on this next slide, which really depicts this as a competitive binding assay. So for example, if someone is positive for onchocerciasis, they'll have these little yellow balls here, which represent NATOG. And if you're negative, you won't have those. So in the first phase, you can see the urine flows across, has all these different entities in them. But in the positive individual, the NATOG that's in their urine will bind up these antibodies. And then when you move on and they flow across the rest of the strip, you can see that these will flow right over because they're saturated. And then these antibodies here that don't have NATOG in the urine sample will then bind the test line. And since we've coated them with this visual indicator, these red dye, basically, they'll turn the test line red, and we can visualize where they are. So again, here's a great tool. It's readily available. People have used this. Now, what's the problem? Well, of course, we need to have these antibodies. And before I got into Scripps, I didn't even know you could develop small molecule antibodies. I'd only really been familiar with antibodies for viruses and proteins and things that are much larger. And one reason for that is it's difficult to make antibodies for small molecules. You actually have to trick the immune system. So here, in our case, you need to make it look like the small molecule is part of a larger thing. And to do that, we take NATOG, we take some sort of reactive group, and we link it to a carrier protein. That way, when the immune system goes, attacks this carrier protein, it will break it up into a bunch of little pieces, and it will make antibodies for all these small components. And because we've coated this thing with NATOG, it will think that's part of the protein and will also make antibodies for that. So just a view of the structure, for example, you can see NATOG here has introduced a linker, and then you attach that to KLH, which is a foreign protein that will rapidly and often give off a very strong immune response. And now that you have this, you can inject it into mice. They'll have some sort of immune response, which can be seen in their B cells. These are the cells that generate antibodies. You go ahead and fuse them with melanoma cells to make these a mortalized cell line that will also produce high levels of antibodies. And then you can screen all those cells to pick out the ones you want. Of course, you're going to have all sorts of antibodies in this mixture, but we only want the ones that bind NATOG. So to do that, there's a technique called ELISA. It's very simple in the concept in general. You're basically just trying to dilute something over and over again until you can no longer find out that it's binding. And if it takes a lot of dilutions, then you're pretty sure it's binding very tightly. So that's kind of seen here. We put NATOG down, we see how strongly the antibodies bind it. In this case, you just need to dilute it somewhere between 128 and 256, and you start to lose your limit of detection here, you start to lose binding. And then for some of these tighter ones, you can dilute it all the way to 4096 of the original solution volume, and you can still measure binding at this point, which with this spectrum, we certainly had enough affinity with these antibodies. But the next question is, how selective are they? Of course, there's going to be a lot of other compounds that are competing for this antibody. And if you actually look at human urine in NATOG, for example, it has this sugar here. And this is often seen as a glucuronidation, which is a mechanism for the body to get rid of entities. It makes them more soluble. So it shows up pretty often. And in order to see how selective it is versus a lot of similar structures, we went ahead and did a competitive version of this ELISA. So in this case, these smaller numbers depicted here are tighter binding interactions, and these dashes mean there was no detectable interaction. And for the most part, we see fairly tight binding for these antibodies, but in some cases, like 9B11, it actually had a preference for one of these other metabolites over the original structure. So, that's why it's important to go ahead and screen these and really look at their selectivity. 13F9, for example, while it had activity for these other entities, it was such a great binder for the original compound that it was our primary candidate, although we explored two others as well. So then the real development phase is actually a very empirical process. I won't bore you with the details of me playing around with urine basically for a month. And, it was a fun experience and you get used to it. But this is very empirical. You change out these conjugate pad components, you change the membrane. This membrane will determine how quickly the urine flows across it. You modify or change the concentration of these antibodies and which one you use. You can change the same thing for the conjugates. And then finally, do you manipulate the urine in any way? Do you dilute it? Do you introduce new buffers? Do you filter it? Do you change the pH, for example? Using all of this, I went ahead and optimized conditions for this test. And this was the end results. You can see here on the left, when there's no NATOG, there's no competitor. So you get very tight binding to the NATOG that's immobilized on the strip, and you can see that by this color. And then you go all the way to the right where you start to introduce higher levels of NATOG, and you can see this color starts to fade as it's getting competed off by NATOG in the urine. And I was hoping originally for a binary response, right? So NATOG is present, you get a really strong competition, and you see no color. And then NATOG's not present, you see 100% color. But it turns out that this sort of linear response is actually really powerful in a way, because it allows you to use things like phone applications, which are actually often used in the field now, where you can kind of take a photo of these strips and then back calculate the exact concentration of NATOG in the urine. So in that way, if you wanted to monitor disease progression, for example, you can keep testing these strips weekly or monthly, and you can hopefully back calculate and see NATOG decreasing over time in that patient. So now that we have this strip, we know it works. You need to be able to set a diagnostic cutoff, right? So what amount of NATOG is enough for you to say this person's infected? So we wanted to increase the scope of the patients then tested. And what we went ahead and did is collect even more samples and from different regions. And then we overlaid the different concentration of NATOG over these two populations. And unfortunately, when we did this, we actually saw a greater overlap between the positive and negative individuals, although there is still significant difference that you can use this strategy. But you can see here, even if we set this cutoff here at 25 micromolar, still 5% of these negative individuals are going to be false positives. And, the majority actually of these positive individuals will be false negatives. And, this could be for a few reasons. There's genetics, there's diet differences. Also, there's really limited diagnostics currently. So it's likely that some of these negative individuals were actually positive for onchocerciasis. But the great thing about the strategy is it's so cheap and so easy that individuals that are infected and perhaps in this region here that are being false negatives, you test them next month, it's likely that their NATOG concentrations are increasing over time because the infection is progressing, and maybe you'll get them on the next test. So it's such an easy strategy. You can overcome some of these limitations. What you really want to do is avoid a lot of these false positives. So then finally, we've created this test, we've evaluated it, we set a diagnostic. How does it compare to maybe a really powerful, accurate strategy? In that case, we wanted to use mass spectroscopy. This is something that's certainly not available and commonly used in a lot of these countries, but we wanted to compare it to something that's extremely sensitive. And in this case, we found about 85% of patients to be correctly diagnosed relative to mass spectroscopy using this approach, which is pretty cool because, I'm making these strips by hand, cutting them, gluing them, pipetting them. It's certainly not the industrial revolution of robotics that exists currently in the field. I mean, I'm nowhere near as reproducible and accurate as those machines. So when we hand this off to a company, which we have, and they're undergoing development, you can assume that this will be a much better result. And that's exactly what we've done. I went ahead and gave this with the whole JANDA lab together and the Scripps Research Institute, the IVD research, and we didn't want to file any patents or take any royalties, and they have complete rights to develop this as they see fit and hopefully get it to people as cheaply as possible and as quickly as possible. And I stay in contact with them and usually correspond every few months to help them along with their development process. Doing all this work, there's a ton of people to thank, of course, a ton of collaborators I can't all list here, a lot of JANDA group members, which I can't all list here, and then, of course, all the companies and research programs and academic programs and fee waivers that helped me get here along the way. And then finally, of course, I got to thank the NSPIRE initiative, all the participating universities, the North County Higher Education Alliance, and all of you who came here and listened to this. Hopefully you found something useful from this presentation that you can go ahead and use in your own life. So thank you very much.